In the past two lessons, we have learned where and how to produce radionuclides. But how do we know whether the product is any good? In other words, how can we assess radionuclide quality? Let's look back at the different steps involved with the production of radionuclides. The first step is to get your target material and pack it into an appropriate target container for irradiation. Then the target is irradiated in either a research reactor or an accelerator for a specific amount of time. The next step is the separation of the produced radionuclides from the bulk target material, which we'll cover in more detail in Module 4. And after we have separated the product, we can send it off to end users, which can be a hospital, for example. However, there are often very specific requirements about the product quality which must be met. Therefore, we will look at three different indicators for product quality: the specific activity, the radioisotopic purity, and the radionuclidic purity. First, specific activity. The specific activity, according to radionuclide producers, is defined as the activity of a radionuclide divided by the mass of the sum of all radioactive and stable isotopes of that element. If we write this definition as a formula, you see that to calculate the specific activity of your sample, you just divide the activity in becquerel or curie by the mass, which can be in grams or moles. In the ideal case, you would have no stable isotopes remaining in your product radionuclide sample. This means that all atoms of that element in your sample are the radioactive isotope of interest. If that's the case, we speak about the theoretical maximum, or carrier-free specific activity. This can be calculated by multiplying the decay constant with Avogadro's constant divided by the molar mass. You can imagine that from an application point of view, the producer's definition of specific activity might be a bit narrow. If you're looking to use the radionuclide to label a radiopharmaceutical, it also matters whether there are any other elements in the sample that might interfere with the labeling, for instance because of similar chemical properties. A more useful quantity in that case is the effective specific activity. It's calculated in the same way as the specific activity, but then the mass also includes chemically similar elements. The definitions of specific activity that I've introduced are from a radionuclide producer's point of view. It's good to be aware that although the concept of specific activity exists in different fields, the definitions behind them can vary a lot, resulting in very different specific activities for one and the same sample. We have covered the two definitions used in radionuclide production. But when you talk to colleagues in the radiopharmaceutical community, they divide the activity by the mass of the entire chemical compound, rather than just the element. And in radiological health physics, the specific activity is calculated by dividing the activity by the total mass or volume of the solution. This means that if you have your radionuclide product and you dilute it in pure water, according to radionuclide producers, the specific activity remains the same, but according to the health physicist, the specific activity decreases by a lot. With the specific activity, we have looked at the contamination of your radionuclide product with stable elements. However, we also do not want our product to be contaminated with other radioactive elements. The radionuclidic purity describes the presence of radioactive isotopes of different elements in your sample. For example, look at the proton irradiation of zinc nitrate targets to produce gallium-68. Both the zinc, as well as the nitrogen and oxygen in the sample, are activated by the protons. And next to the gallium of interest, we also produce radioactive zinc, copper, carbon, fluor, and nitrogen. Since these radioactive isotopes are different elements, we can get rid of the impurities through chemical separation, which we will discuss in Module 4, or in the case of short-lived radionuclides, by simply waiting until they have decayed. A final important measure used to quantify the quality of your product is the radioisotopic purity. This plays a role when you're producing several radioactive isotopes of the same element during your irradiation. For example, when you irradiate a natural abundance platinum target in a nuclear reactor, there are 6 different stable platinum isotopes that can capture a neutron, which can result in quite a lot of different radioactive platinum isotopes. If you want to produce platinum-191 for medical applications, you would rather not have the long-lived platinum-193 with a half-life of 50 days contaminating your sample. You could increase the radioisotopic purity of your sample by using enriched isotopes. In our previous example, if our target would have consisted of only platinum-190, then the neutron capture reaction would only produce platinum-191. In the case of short-lived impurities, you can wait until they have decayed. You might also attempt to separate the different radioactive isotopes of the same element, but this is very difficult or sometimes even impossible to do. If you're interested in how you could still separate these, you should check out the advanced topic of this module. Now that we've learned about different ways to assess radionuclide quality, it's time to start with the exercises. Good luck!